Okay, so for Unit 9, Unit 9 is all about entropy. So for question number 1, I want you to look at A, B, and C and tell me whether or not entropy is increasing or decreasing. So you need to know that entropy means disorder. Okay, so how disordered is the chemical compounds or particles themselves? So for this, if you go from a solid to a liquid to a gas, your disorder increases. And entropy is change in S. That's the symbol for it. I know it kind of doesn't make sense, but that is what it means. So entropy increases if you go from solid, liquid to gas. It also increases if you go from fewer moles to more moles of gas. Okay, so the key word is gas, so you have to look at the gas. So fewer moles to more moles of gas. So you should be able to look at these problems here. Now in C here, you notice that you have a solid, you have a liquid, you have a solid, and you have a gas. So for this one, you should be looking at number of moles of gas when you have a whole bunch of phase changes. For A and B, you only go from, it's like one to a different phase. So it's not like multiple phases all in one problem. Okay, so that's for number 1. Now, number 2, entropy, change in S, can either be positive or negative. Okay, so if change in S is positive, that means there's more disorder. And if it's negative, it's less disordered. Okay, so typically we want it to be positive because typically in life everything is becoming more disordered. So I kind of drew different phases of molecules. So kind of look at that. So for this one right here, you might want to look at moles of gas. And then hopefully you can tell in A here, maybe 1 is a different phase. So like liquid, solid, gas by the particles, kind of how they look. So see if you can do that. For number 3, I want to know which one has the most negative change in entropy. So remember, depending on the sign, so change in S, if it's negative, try to figure out which one is more disordered. So again, use the front side. Like I said, if you go from solid to liquid to gas, change in S also increases or more positive. I should write that down there. For number 4, oh, you would have to look this up in your textbook, or I'm just going to give them to you. So if you watch the video, I guess you'll get them. Iron is 27.15 joules per mole Kelvin. Oxygen gas is 205.0 joules per mole Kelvin. And Fe2O3 is 89.96 joules per mole Kelvin. Now for this, it is just like change in H. So you're going to do change in S equals products minus reactants. So again, make sure you pay attention to how many you have. So it's just like change in H. So basically, here's your product. You do 4 times that number minus then all your reactants. Okay. Then I say justify the sign. So tell me, is it positive or negative? What does that mean? Is it becoming more disordered or less disordered? 5, I say explain why the reaction has a negative change in S, where reaction 2 has a positive change in S. So you might want to look at moles of gas. Okay, so remember, the more moles, if you go from less moles to more moles, your change in S is positive. If you go from more to less, it is negative, just from the stuff on the front there. For this one right here, for number 6, there's something called change in G. So change in S was entropy. Now for change in G, G is kind of funny. It is called Gibbs energy. So I'm going to label that. So that's Gibbs free energy. Okay, so what that is, it kind of tells you how everything is going to react. Okay, so change in G, if it's negative, that means it's spontaneous overall. And if change in G is positive, that means it is non-spontaneous or not spontaneous. Okay, for the reaction, now you might be asking like, well, isn't change in S? It's kind of the opposite of change in S, and yes, it is. Gibbs energy kind of gives you more information because you can actually relate a whole bunch of stuff to it. So for this one right here, for number 6, standard conditions, what that means is that 298 Kelvin, that's a temperature. It's always at 1 ATM. Okay, so those are just standard conditions. So for this problem here, you have to use an equation. It's change in G equals change in H. I like to put little circles after that, just means it's in standard. So when it says standard, those little circles mean it's just standard state. Temperature times change in S. Okay, so what you can do, I give you change in S, I give you change in H, so you basically have to plug those numbers in. However, change in G is actually what I want you guys to find. I want you to find it. It's actually in kilojoules. Okay. So that means change in H, when you plug it in, this number is good because the units are in kilojoules. But for change in S, it's actually in joules. So you're going to have to change that. So 1,000 joules equal 1 kilojoule. So before you plug change in S in down here, you have to change it. Okay. For this one, you're just going to rearrange the equation up here for temperature. So you're going to do temperature equals change in H. Oh, shoot, it went out. I hate when this happens. Oh, hang on. Why does it do this? It's so stupid. Oh, gosh. Oh. Okay. Change in H divided by change in S. Okay, so when this happens, when you're finding out for the temperature, technically change in G equals change in H minus T change in S, and that all equals 0. So that means you are just going to, for the temperature to solve for it, you're just solving for the last part here. So it's change in H over change in S. So basically going to plug that stuff in. When you do this, you're going to get a temperature. Okay, and once you get that temperature, that will be the answer. Okay. For 7, you have to find change in G given those values in your textbook. I'll just give them to you right now. But again, the equation that you're going to use is change in G equals change in G of the products minus the reactants. Okay. So it's just like how we've been doing change in H and then the change in S1, which is on the previous page. So for this compound right here, the value is negative 1576.5 kilojoules per mole. H2 is 0. Al is 0. And then H2O is negative 228.6 kilojoules per mole. Okay. Now, one thing that I want you to know, if change in G is greater than 0, so that means it is positive. That means that it's not favorable. So that means the reaction won't happen spontaneously. Okay. That's all you need to know for that one. Okay, so products minus reactants. Then for this one, it says a chemical company claims that they are able to produce a certain product through a thermodynamically unfavorable process. Explain how this is possible. So if it's unfavorable, that means that it's probably not going to likely happen. But here you go for the notes. Now you can look this up in the packet before the PowerPoint slides, and it says it all in there. Okay, let me spell this word out. If it's unfavorable, that means the reactants are favored. And the reason why is because it's not going to go to the products. So you're not going to get your products. So when you're unfavorable, the reactants are favored. However, if you are favorable, meaning it will happen, that means that products are favored. Okay. So I kind of want you to tell me, why do you think it still happens even though it says it's unfavorable. So at equilibrium, that word again. At equilibrium, I want you to kind of, if you can, I don't know if this is going to help you or not, but the concentration brackets. Okay, so at equilibrium, concentration. So if it's unfavorable, will the concentration favor the reactants or will it favor the products? So if it favors the reactants because it's unfavorable, okay, what does that mean for the concentration of the reactants at equilibrium? Will it shift towards the reactants or products? So that's kind of what you're answering here. There's that question. Now, we'll see if you can kind of answer that, and that hopefully will answer the last question. So hopefully this helps.